So in this video, I'm going to be speaking with Professor Phillips. He's a professor of physics at the University of Illinois. He's also a theoretical physicist. I first met him during my senior year at the University of Illinois. I took a class with him called Space, Time, and Matter, which looked at our current understanding of reality through a philosophical and physical lens. I want to preface this video by saying that I am by no means an expert on physics, or I didn't study physics. I'm just someone who's passionately curious. And if this is something you're interested in, then stay tuned. I'm going to start off with just talking about your background.
Okay.
Why physics?
Why physics? Okay, physics. I was very taken by English in high school and math. And so I like stories. And theoretical physics is a way of telling stories with math.
Okay. What about your journey? So I think you brought up how in high school you didn't do very well at
Right, I didn't do
courses.
very well at all because I don't know what your high school was like, but mine, boy, the classes were not very mathematical. If something gets more mathematical, then I tend to do better. And that's the opposite of most people. I think you have to have... Physical intuition is hard to develop. Whereas if you give me an equation or tell me how you think about it mathematically, I can follow that just perfectly. So when I got to college, the explanations were much more advanced. And then I found, oh, is that what they were talking about? For me, physical intuition developed later. But I sort of had to force myself to develop physical intuition. So I relied a lot on my math ability.
Okay. So what about philosophy? I know that was something you majored in when you were
Well, I didn't
at
major
college.
in it.
Oh, you
Okay,
didn't?
so
Okay.
no, I didn't major in it. My father is a philosopher.
Oh, okay. I didn't know that.
Okay, yeah,
Okay.
most people
That
don't.
explains a lot. Okay.
So, in
Okay.
fact, we were just in Walla Walla celebrating my father's 90th birthday.
Okay. Wow.
And one of the things I brought up is the fact that from a very early age, I was exposed to philosophy.
Yeah.
So, and philosophers tend to bring their work home.
I'm sure there's a lot of lessons that carry over.
So I was familiar with Gruen-Blien.
Yeah.
Well, I knew what it was.
Yeah.
I'd heard the words when I
Okay.
was 11.
Yeah.
I did not know what they were until I started teaching this course.
When you first brought that up in class, I was like, "What? How does this relate to anything that we're talking about at all?"
Yeah, I mean, in preparation for the lecture on Kuhn, I started doing all this secondary reading. And of course, you run into the paper by Nelson Goodman on categories.
Yeah. Yeah.
How do you know when something has really changed?
Yeah.
You walk by a bush one day and it has red flowers. The next day, it just has green leaves. Well, if you know about the progression, you know that's not an oddity. And that's what Gruen-Blien were trying to capture.
Yeah.
And I had no idea what they wanted. I mean, who knows what Gruen-Blien are?
I remember. Yeah, I forgot the logic behind each one, like the rules.
Yeah, Gru is green before a certain time, blue afterwards. So when you see that, you don't view it as a discontinuity.
Yeah.
So someone who knows about Gruen-Blien or sees things that way could conclude that all emeralds are Gru, rather than all emeralds are green. And when they see the change, they don't view that as, oh, I need a new paradigm. Just like we don't need a new paradigm when we see caterpillars and then butterflies.
Yeah. Yeah.
So Goodman's point is that we can see sort of methodological changes, but it depends on the categories that we have in our heads. And that was the big advance of Gruen.
And there was one of the paper topics involved.
That was one of the paper
Right,
topics.
yeah.
I mean, I don't think anyone wrote on
I mentioned it in my paper, but I didn't really go into depth.
Yeah. Yeah. So, right. I mean, that's a great topic. And it's one of those things in philosophy that when it came about, people went, oh my God. Well, it was a major thing because it's sort of stated in a... The meaning is obviously hidden because you have no idea what the hell he's talking about. But there you go.
How do you apply philosophy to your work? Does that motivate you a lot?
Absolutely. The questions I ask, what I view philosophy as is it helps you ask much better questions. And the questions I ask in my work, I don't think I would be asking if I hadn't had a background in philosophy. So when I went to grad school, I started taking grad classes in philosophy. I'd taken a couple of classes as an undergrad, and then I thought, I know what's going on. I'll take grad classes. Oh my God. That was very, very difficult.
Those are hard, yeah.
It's all grad students, and they can talk about this stuff, and the secondary reading is just not easy.
Yeah.
And so, I have to say that I probably did this because, I'd been taught philosophy by my father since I was very young, so... But that's very different than taking a class and then reading all of this secondary stuff. Because when you read stuff by Stalnaker, I still remember all of that stuff on the identity of persons, and oh my God, it's just very difficult stuff.
Yeah.
It's at that point I realized I'm not really a philosopher. I can understand some things, but I'm not a philosopher.
It's difficult because it's entirely questions that can't be answered, but can be logically
you can
deduced.
Formulate them.
Yeah,
that's right.
Yeah.
That's right. And so that's how I view it. I'm interested in the questions, obviously, and I sort of... But it's really because of my exposure as a kid with my father.
Yeah.
That put me on a track to... not take things for granted.
Yeah.
And always trying to get at the answer.
Deeper thinking.
Deep thinking. I
First principles thinking.
Yeah, so there's no way I could have avoided that. But, it's interesting.
Yeah.
I'm the only one of my siblings who gravitated to that. All of them were just absolutely bored by it. Absolutely bored by it. Okay. So, it's one thing to be exposed to it. You have to have an interest.
Yeah.
And so...
Okay. Well, moving into some more, physics, I kind of broke down these questions into, 3 different parts. Classical, quantum, and then unification theories and other mysteries.
Okay.
So I don't want to spend too much time because there's a lot of questions.
Yeah, there's a lot of questions here.
All of them. And we can talk about this forever, probably.
This is the whole universe here. Okay?
So, we're going to talk about light.
Light.
What is light?
Light's a spin one field.
That's the simplest way.
That's the mathematical way of formulating what light is. It's like gravity is equivalent to every statement about a spin 2 field is a statement about gravity. You can reduce gravity to a spin 2 tensor problem.
Can you describe
But
it?
that doesn't really tell you what light is.
In a less technical way.
Okay. If I'm not teaching the class, that's what I'd say. Gravity is a spin 1 field.
Yeah.
Sorry, light is a spin 1 field.
Yeah.
Okay, so light. See, this is where philosophy doesn't help you.
Yeah. This is where there's a very technical answer.
Yeah, the very technical answer. So I think you would just have to say that you cannot understand light as a phenomenon in just electricity or a phenomenon in magnetism. It's the union of the two.
Yeah.
It's an emergent phenomenon.
Maxwell's
synthesis. Okay? So the synthesis of both of those is light. There's this propagating field, perpendicular E and B fields, and...
I'm thinking of the diagram.
Yeah.
They're like...
Yeah, they're like,
Yeah.
yeah, right,
Yeah.
okay? That's what light is. It's a combination of the two.
What happens if you ride a light beam?
Time doesn't progress.
Really?
I taught you that. That's what
I'm going to get
Einstein...
into.
That's what Einstein wondered.
Yeah.
What would happen if you rode a light beam? What's interesting is that I used to be obsessed with that question as a child.
Yeah, you told me about that. Yeah.
I told you this when I taught you the class.
Yeah.
And so I'd forgotten that Einstein thought about that question. Of course, I didn't come up with anything interesting, but that sort of thing was. So I knew from very early on that was the direction I was going in.
Mm-hmm. And time has to stop, or not stop, but run slower, because the speed of light is independent of every observer.
See, I'm not sure you could deduce that entirely from that.
Okay.
If
I were to describe to someone, that's what I would say.
Yes, that's right. But the thing of it is, we know one thing.
Mm-hmm.
If, in fact, there was just Galilean invariance, you could never explain why it is that two observers measure the same speed of light.
Mm-hmm.
So there's a symmetry property, which completely removes your velocity. Okay?
Yeah.
Now it turns out that a consequence of that is that time slows down.
How radical was this?
Oh, it's incredibly radical.
At the time it came out.
I mean, no one was thinking like this.
Newton's static universe was thrown out the window.
Hold a minute.
Not initially, but...
the fact that, Newton really emphasized that there is a way of... Well, so Newton really emphasized that there is a preferred frame, so that, he knew that his equations were valid, that in terms of measuring velocities or positions, nothing in the equations depended on any absolute position or absolute velocity.
Yeah.
It was always a difference. But he didn't like that.
Yeah.
See, just to formulate the equations of motion for classical mechanics, you have to solve the problem of relative to what. Remember we talked about this.
Yeah.
The which train is accelerating problem when you're sitting on a train and you look and say, oh my goodness, am I moving or is that other train moving? You pick a reference frame and then you see, oh, I'm not the one moving. Okay? But Newton knew it didn't matter. But he was determined to settle that with a frame which was fixed. Okay.
The ether?
The ether. Okay?
Yeah.
Now, you could have said, okay, but Michelson and Morley sort of got rid of that, that, light is carried on something and that's the frame that's fixed. But the fact that we couldn't detect it, and remember, that was a question on the final.
Yeah.
Poincaré, what did he say? Perhaps the indetectability of the ether is a principle of nature itself.
Yeah.
And then I asked you guys, is that
Aristotelian?
Is that Aristotelian?
Yeah.
And is it similar to how you resolve the...
AMPS? No,
not the Amps paradox, but it was the...
Was this the vacuum energy?
Yeah, this
question?
was the vacuum energy, the string theory landscape problem.
Okay.
Which I admit was a very difficult question.
I totally forgot what that even was.
Yeah, because I did it one day, and actually I did it on the same day that I did anthropic principles.
Okay.
That's when the landscape problem comes up.
Yeah. Okay.
Right.
Okay. So the transition from special to general relativity, there's an elevator involved somewhere in there.
There is an elevator
There's a falling
involved.
man in an elevator.
Yes.
And the equivalence of acceleration and gravity.
Right.
Explain that.
Okay. So, Einstein, the problem with gravity is that, as Einstein would have said, and that's the problem that is the inherent problem with gravity, is that you can't get rid of it.
Yeah.
Everything feels gravity.
Yeah.
E and M is completely different because you just neutralize the charges. Go to it. You can easily get rid of them. You can't get rid of mass. It's just there. And that's because mass breaks scale invariance. Okay. The existence of charge doesn't break any symmetry. Okay.
Symmetry.
There's no symmetry principle. Meaning this is very important.
Yeah.
There's no every time you break a continuous symmetry, there's a conservation law. And a continuous symmetry is just formulated in terms of local differential operators. Like linear, and that's Noether's theorems.
Can you give an example?
Right.
A very simple example.
Okay, the simplest angular momentum, for example. Okay. Conservation of current. Okay. If you look at electricity and magnetism, electricity and magnetism is redundant if you formulate it in terms of E and B fields which are independent. And people knew that. Faraday, okay?
Yeah.
Moving B field creates an E field, okay? So there's clearly some relationship between them. And so in electricity and magnetism, this is represented as a gauge symmetry.
Yeah.
Remember I told you guys about gauge symmetries. These are mathematical symmetries.
Yeah.
And you can think about them as the position of the hand on a clock.
Okay.
Okay?
Electricity and magnetism?
Yeah, so in that, what we see is that there's a more fundamental description of electricity and magnetism. You can replace the E and B fields by another entity, and it gives rise to both of them. And as a result, the equations of electricity and magnetism have a degree of freedom associated with the redundancy of the E and B fields.
Okay.
And that gives rise to a conserved current.
Okay. That's a very technical answer.
It is a very technical answer.
I'm not sure if I understand all the details of that, but the general idea.
For example, time translation symmetry gives rise to conservation of energy.
Yeah. Okay.
Okay?
Okay.
Okay, that's the simplest one.
So, general relativity, going back to...
Right. How did that, the falling...
The elevator.
The elevator. Okay. So what Einstein said is the following. He was asking you, how do you really feel gravity? And the answer is very shocking. He said, if you completely expose yourself to gravity, you don't feel anything.
Yeah.
And that was the whole point. It's sort of the opposite thing that you would have thought. In other words, if you were to fall off a tower, and let's say it's a long distance you're falling, you seem weightless to yourself.
Yeah.
And from that he concluded that no local measurement can ever tell you you're in a uniform gravitational field. You'd have to fall a distance comparable to the radius of curvature of the thing that's causing the gravitational field for you to detect anything that you were in a uniform gravitational field. So then he said, aha, now let's take this person that's falling and surround them with an elevator. And now let's put an engine on this elevator. And then so the engines start up.
It's accelerating upwards.
It accelerates upwards.
It's the same as...
The elevator catches the person's fall.
Yeah.
And it's as if they can't tell the difference between standing in an elevator at the Sears Tower or this room right here that you've surrounded the person with. You've simulated gravity,
Yeah.
holding your feet to the floor with the acceleration of a rocket.
This is something that I used to think of when I was younger. Because I had a trampoline in my backyard, and if I was holding something and I would fall, when I'm jumping, it would float.
Right.
And I was thinking,
Actually, it wouldn't really. It would keep on falling. It would keep on
but we're
falling.
falling together.
Yeah, you're falling together.
Which is the same as being weightless.
In your frame,
Yeah.
it would be.
Well, that's the relativity part of
That's right.
relativity.
That's right.
Yeah.
That's right. So Einstein said, if two things seem the same, well, they are the same. Mm-hmm. And hence every statement about gravity is a statement about acceleration. Mm-hmm. And
so that simple idea became general relativity, which describes a field, space and time being a field, and a field is just something that exists forever throughout, expands forever throughout.
So the
universe.
Key thing here is the fact that in if you can't tell the difference between falling, I mean, if you can't tell the difference between the rocket ship on the elevator and gravity, then, and you can't determine if you are uniquely in a gravitational field by making a uniform gravitational field, by making a local measurement, then gravity is about something very, very big. It's not about any local sort of thing. Okay, and hence it has to be about geometry. That's the biggest thing we know.
Yeah.
Okay, so that is really... So then we say that gravity really isn't a force.
It's
the
bending of space.
It is,
which is...
It's really a construct that comes from how matter mediates this fabric that we call space-time.
I think it's interesting how light plays such an important role through all of Einstein's work. And specifically when he unified time and space into one, we call it a fabric, I guess, for simplicity.
Yeah, that was one of the things that Einstein concluded, that, gravity slows clocks down. Look at how he came up with special relativity.
Yeah.
It was really understanding what we meant by simultaneity.
Two events happening.
Yeah, what does it really mean for us to record two things?
Yeah.
They're occurring at the same time. Okay.
So...
And then he saw that if one frame is just moving relative to the other with a constant velocity...
Yeah.
There is no agreement. Okay.
So this is considered a classical theory. Why is that?
It applies to the very big.
Okay.
That's what if you were... The layman's definition of classical is that it applies to the very big. It's classical in the sense that we can use... either Newton's equations or general relativity to completely lay plain everything about them. There's no further fact that we would need to explain.
Okay. So, transitioning to the less classical world, can you describe what quantum mechanics is? Simply.
Simply?
In a not so technical answer, but I'm sure it's hard to explain without some technicalities.
So when it comes to the very small, we find there are things that don't seem to mesh our classical understanding.
Okay.
And that lack of meshing is where quantum mechanics comes in and tells us how to think about the very small.
Mm-hmm.
And when you think about that, the big surprise is that there is even a classical world. I think I've mentioned this, that if really all of the small stuff has this inherent quantum mechanical uncertainty associated going on, then why does this go away at the large level when we don't need to worry about any of this?
That was one of the first questions I asked you when I
that's right.
Where's the line between the quantum world?
Well, it turns out it's just a continuum. I mean, and so it really, I mean, you are a discrete object. However, I could resolve your wavelengths, but they're so tiny, it's unresolvable. The quantum world, I mean, the microscopic world, the subatomic world, the wavelengths can be resolved. And as a result, we can see the wave-like properties of an electron. We can also see its particle-like properties. You just have particle-like properties.
So going back to, let's like dig into that answer a little bit. So like, you mentioned uncertainty. So Heisenberg's uncertainty principle.
Right.
We can't know the position and momentum of
at any given time.
At any given time. So
with arbitrary certainty.
So the closer we look, the less we know about.
I think the most accurate way of stating the principle is that consider the two-slit experiment. Okay, what did they really teach you guys was the way that you should think about the uncertainty principle there?
That it's impossible to know which slit the particle goes through.
It's impossible to devise an experiment to determine which slit the electron went through without at the same time destroying the interference pattern. Okay? Which and since the interference pattern is a fact of the world, it's an ontological fact of the world. Uncertainty is not a problem. Is not something in our heads. It's not epistemological. I asked you guys a quiz on that.
Yeah, I got that one wrong.
It's an ontological fact of nature.
Yeah.
And hence it's important. It's not just a function of us being bad thinkers or, limited anyway. That's the real way the world, the quantum world is. Okay? So the uncertainty principle, that's really it. And it's something you have to accept on a fundamental level. Our thinking that, it's an electron, it's like a bullet, should go through one slit or the other, the way Feynman lays it out. Feynman's lecture on this is just brilliant. That's how I taught this, actually. I think everyone teaches it this way, because you just got it right. That thinking breaks down. Every attempt, every experiment you can think of, whether it's dimming the light, increasing the wavelength, none of these, taken to an extreme, will be able to tell you what slit the electron went through.
Can you describe the wave function?
And that's actually very simple. Okay?
Yeah.
When I describe you, I say you're here at this time. Okay? Quantum mechanically, I would have to sum over all the possible histories of you.
Okay.
We don't have to do that classically. Quantum mechanically, as Feynman would say, I have to sum over the histories.
Meaning...
And these histories you can think about as superpositions. Okay? So there would be a linear superposition. And that's why you have to think about the electron going through the two slit. The sum of an amplitude going for one and the other at the same time. So all of the mutually compatible descriptions of a system we have to treat on the same level.
Mm-hmm.
We don't have to do that classically.
Mm-hmm.
One is selected for us.
So the wave function describes the probability of finding
No, it doesn't. It doesn't.
No,
The square of it does.
Okay.
Okay. So the way that we think about the wave function in the Born sort of approach is it tells you a probability amplitude, an amplitude for something to happen. But to get a probability, you need to sum up all of these amplitudes, square it, and when you do that, there will be cross terms between them. It's not just the sum of this plus this. And as a result, the actual probabilities will be less than what you would have thought.
You know, it's kind of mind-blowing when you think that on a quantum scale, things don't exist until you observe them. How do you think about that? Does objective reality exist on quantum scales?
So I think the real question is, does objective reality exist? Not subjective reality.
Sorry, yeah.
Okay, so there is no objective reality in quantum mechanics. And which is why the quantum realm is much more shocking than general relativity or special relativity.
Yeah.
Einstein came up with that, completely confirmed. In his lifetime, Einstein was perfectly justified in doubting whether or not these principles of quantum mechanics were true. Because local hidden variables Bell hadn't done his work.
Yeah.
It was perfectly reasonable to say, I'm not sure that's really the way the world is.
Yeah.
And he never accepted it.
Yeah.
Not that that's the way Einstein necessarily worked. If you look at... it's sort of a long answer.
Yeah.
If you look at how he came up with special relativity and general relativity, it's not as if he was guided by experiments.
Yeah.
Okay? He really said this is the way it should work.
Yeah.
If you look at his photoelectric effect, he saw that there were sparks and things like this, but he's the one who made the leap and said, he went beyond what Planck did. So it's not the interaction of light with matter that's quantized. Light itself is quantized.
Yeah.
And remember what Planck said about that. He thought he was crazy.
Yeah.
Okay, and that was a big step. So it's not as if Einstein needed experiments to make statements. But with quantum mechanics, that was a bridge too far for him.
Yeah.
And it wasn't that, experiments didn't seem to confirm what was going on, in that there really was no way of telling which the electron went through, or that there was this inherent uncertainty. I mean, there was enough. The way I look at it, if Einstein could have done general relativity just by reasoning through equivalence principles, I don't see why he didn't accept quantum mechanics, a la Bohr. Okay, because it's not as if he was really an experimentally oriented theorist.
Yeah.
He just reasoned through things and various thought experiments, and he arrived at answers.
Okay.
That has always been a big mystery to me. Why is it Einstein, this guy who relied on sort of pure thought, he was able to look at something like simultaneity and see that we would record different results, and reach the conclusion that time has to be dilated. I don't see why he couldn't have accepted quantum uncertainty, but we all have blinders, That's the only way I look. It's my only.
So, this was a term topic. This was one of the, not the term topic, but a paper was about, does objective reality exist on
Does objective
quantum
reality
scales?
exist? And the answer is no.
Yeah.
I mean, that is the world we live in now. I mean, it's now absolutely clear. The Nobel Prize was given for it a few years ago. Right. And if we look at any attempt to put objective reality or realism into quantum mechanics, we know that at the level of local hidden variables, that's not consistent with anything we see experimentally.
Yeah.
And we don't even have to worry about the Bell inequalities.
Yeah.
Just do a single experiment on a 3-photon state, these Greenberger, Horn, Zeilinger states, GHZ states. I mentioned this in the class.
I don't. Yeah,
But
I'm
never
not familiar.
The math is sort of beyond what is possible in the class, but a single measurement on 3-photon state can tell if it's local hidden variables or quantum mechanics. And that experiment has been done.
Yeah.
Local hidden variables is completely out the window. Quantum uncertainty is the way the microscopic world really works.
So, do different interpretations of quantum mechanics attempt to bring objective reality?
Some do.
Yeah.
Some do.
Like the many worlds.
The many worlds theory.
Yeah.
I'm not that big a fan of many worlds. I know it's sort of fashionable now, and people are
in media and movies. They like to.
You're right, the multiverse.
The commencement ceremony. I don't know if you were there, but someone made a reference to that. Yeah.
Really?
The dean of the business school said, "We're the best business school in the multiverse." Or something.
Yeah, it
Yeah.
I mean, when things get to that level, physics has been successful.
Yeah.
I think physics is probably the most successful of all of the, fundamental sciences and sort of giving people stuff to talk about.
Mm-hmm.
I mean, biology has been pretty successful.
Yeah.
DNA, that's an expression. Well, it's not really part of my DNA, is it?
Yeah.
Easier concepts.
What interpretation are you gravitate towards?
I gravitate to most.
Or do you think is most backed up by experimental evidence? But I guess that's a hard answer. It's a hard question to answer.
No, that's a fair question. I would say, some version of my puzzle is the collapse.
Okay. The wave function?
Yeah. And
go back, sorry. When the wave function collapses, that's you're observing it.
Yeah, that's right. But in the Bohr interpretation, it was always outside.
Yeah.
It's not part of the quantum mechanical theory. So I think those who are trying to come up with nonlinear terms that collapse, that are part of the whole Schrodinger thinking, or at least appending to the Schrodinger equation, things that involve the collapse. I think those approaches are the ones I'm most grounded in, I would say. I think those are I think that's the correct way to think about it. Because it's not satisfying that ultimately the collapse of the wave function, which we know happens, isn't part of quantum mechanics.
Yeah.
So I think there has to be a way of seeing that in the equation itself.
What are examples of that interpretation? Or interpretations that...
Well, so
that
these theories aren't all that formulated, but they're attempting to put in non-linear terms in the Schrodinger equation, and to see if that can induce measurement.
Mm-hmm.
And so that's an ongoing thing. It's not something I am working on, so I sort of read about this from time to time, but it's not... You have to pick your battles, and the stuff I do pretty much occupies all my time. So
Yeah.
But that is, if somebody would ask me, as you are asking me now, I would say these collapse theories that try to put in extra terms into the Schrodinger equation, that's where I think the answers are.
Okay. So going back to Einstein and his refusal to accept quantum mechanics,
Yes.
specifically with his disagreements of entanglement and how that broke simultaneity. Yes. Did I phrase that right?
I don't think it had to...
Or the causation, I should say. It broke the speed of causation according to general relativity and...
Well, okay, so remember now, there's no energy being transferred, so it didn't matter that you could know exactly what the photon is doing in Paris when you measured it in, Sierra Leone. There's no problem with causation there. Mm-hmm. And by causation, I mean something that is limited by the speed of light, because you aren't sending a signal.
But
you could know instantly.
Information
But information
transferred.
But it's not transferred. It's just transferred over a physical distance.
Yeah.
It's just something you know.
So it's like the gloves in the box.
Yeah. That's right.
As
right.
Einstein thought
it isn't right. It's not as if there is energy moving from one place to the other, and that's how you find out the information.
Yeah.
That's what we mean by information transfer. Some energy moves from one place to the other. That's not going on here.
So when you described entanglement and why it happens, I was kind of unsatisfied.
Okay.
With the answer. I think you said something along the lines of they're always entangled. Particles are always entangled with one another. But how do you find the entangled pair if they're separated by distances, great distances? How do you know that is the pair if it's only one pair that it's entangled with?
Okay, yeah, that's the monogamy of entanglement. So remember, to do this, it really requires a huge Gedanken thought experiment in which you prepare EPR pairs very delicately. Mm-hmm. So you wouldn't. It's just that all of these experiments, and this is how really what the Nobel Prize was awarded for, that you could fiber optic cable that's that from here to wherever, you could determine the partner photon or the partner electron that was, that is the quantum complement of the other. Okay, so I mean, all of these experiments are incredibly well designed. So it's not as if it's a limitation to know the entanglement. You could you just have to be incredibly careful.
Yeah.
So it's not beyond us. But if it's just a bunch of stuff, you don't know. But now let's just try to construct an experiment that's careful enough that we could know the partner. Then you can do it.
Okay. So going back to EPR, could you describe, what is it, Einstein,
Podolsky, Rosen. Okay,
so what was their gripe with quantum mechanics? And
their gripe with quantum mechanics.
What does hidden local variables mean?
Okay. So here's what they said.
Yeah.
They said, this quantum theory is fine, but we don't think it describes reality because the paper starts with the definition of realism. If, without disturbing a state or measuring it, there is a certain amount of objective reality associated with that thing, then we call that realism. Okay, so it seems like a reasonable thing, and you walk into somebody tells you the room is yellow, if some of the state is not observer dependent, then we say there's a certain level of realism associated with that. What they were trying to show is that quantum mechanics actually had realism.
Yeah.
That it had an objective reality.
Mm-hmm.
So what they did is they said, consider a 2 electrons atom.
Yeah.
2 electron atom,
Mm-hmm.
so only one orbital. One of the electrons has to be up, the other one's down.
Mm-hmm.
Okay? Now let's zap it. Let's send one electron this way, the other one goes over there.
Mm-hmm.
I have a detector over here.
Mm-hmm.
And then they said, once I know this one, I know what this one is.
Mm-hmm.
I haven't measured the one over here.
Yeah.
Hence, there's a certain level of objective reality associated with that one.
Mm-hmm.
And then they went on even more. And they said, well, this thing could be really far away. Well, doesn't that sort of violate the principle of locality?
Yeah.
Then they went and did something more. They said, aha, let's pick another. Anytime I figure out where the spin is up, I have to pick a direction to point the magnet.
Mm-hmm.
So let's now point the magnet in a different direction over here.
Mm-hmm.
And I'll see the complement over here.
Mm-hmm.
Well, how does this electron over here know that I chose a certain direction to point the magnet in?
Yeah.
And hence that direction had to be certain all along.
Mm-hmm.
Ergo, quantum mechanics not only is... Yeah, so here's the important thing. Quantum mechanics as a theory which is based on uncertainty is completely fallacious. Because they've just shown there is no real uncertainty.
Mm-hmm.
And so we went through how you would think about that.
Yeah, yeah.
Okay? Now, so then what they were saying is that if in fact this is true, it has to be the thing that really reinstates objective reality.
Mm-hmm.
Is there must be something local going on.
Yeah.
There's a way of thinking about states of quantum mechanical systems
Mm-hmm.
by throwing away all the quantum variables and just doing something classical.
Mm-hmm.
Those are local hidden variables.
Okay.
Okay, and the GHZ examples illustrate that beautifully. In other words, if things aren't determined by quantum uncertainty, then you don't need to worry about these funny things that I talked about in class, commutators.
Yeah.
Okay, that's so if you can just move things around, whatever principle allows you to do that, let's just call that local hidden variables.
Mm-hmm.
So if you just forget about commutators, then you don't need quantum mechanics.
Mm-hmm.
The basis for quantum uncertainty are commutators.
Okay.
What I told you, right?
Yeah.
I mean, so commutators are you do one operation,
Yeah.
you do another one,
Yeah.
you see what the result is.
Mm-hmm.
Then you do the operation in reverse.
Mm-hmm.
Do you end up with the same thing?
Mm-hmm.
Okay?
Okay. So, explain John Bell and how he disproved local hidden variables and why this was an important...
Some people call it the testing Bell's inequalities, the most important experiment ever done.
Mm-hmm.
And I would say I have to agree with that.
Yeah.
Whether or not we live in a world in which there's objective reality or not,
Yeah.
that's a fairly big deal.
Yeah.
Okay? So what Bell came up with, and this was the really big surprise,
Mm-hmm.
is that you could formulate an equation
Mm-hmm.
which would tell you if something besides quantum mechanics was fixing the observables that you are measuring.
Mm-hmm.
And you wouldn't have thought that you could do so in a systematic way
Yeah.
that would boil down to a single equation.
Mm-hmm.
And that's what he did. So he defined correlations between successive measurements.
Mm-hmm.
And he said, look, if something besides quantum mechanics is operating, this correlation can be represented by a certain quantity that's less than 2. If it's bigger than 2, quantum mechanics is operating.
Mm-hmm.
Experiments have been done.
It's bigger than 2?
2.7.
Wow.
It's not like 2.1, it's 2.7.
So this was done in the 60s, correct? This experiment?
Bell,
Yeah.
no. Bell's
We
theorem
formulated
was
it
really
earlier.
formulated in the 60s.
Oh, okay.
He was at CERN when he did this.
Yeah.
I don't really know why he was at CERN. Let's just say he was there.
Yeah.
And he formulated this, and he was interested in foundations of quantum mechanics, and he was allowed to work on it there.
Yeah.
And it really wasn't. Well, what's interesting is that one of the experiments was done in the 60s.
Mm-hmm.
There was a guy at Berkeley who did an experiment who shared the Nobel Prize.
Mm-hmm.
But really, a lot of this stuff was done in the 70s and the 80s that really showed that Bell's inequalities really did.
And this shows that we live in a world where objective reality doesn't exist.
That's what we have
on
to accept.
fundamental scales.
On the fundamental scales, there is no objective reality. That's a big thing.
That is a deep realization.
It's a deep realization.
That'll keep you up at night.
Yeah, that's why some people say, look, there has to be something else. But what's interesting is that the simpler way, and the way I teach this aspect of quantum mechanics, I teach the GHZ states.
Okay.
Because rather than Bell is based on a statistical measurement, successive measurements. One measurement on a 3-photon state gives you 1 or -1.
Yeah.
If quantum mechanics is true, I forgot which one it is. I think it's 1. If local hidden variables is true, it's -1. I forgot which way it is, but it's a sign difference on a single measurement, and that has been done. And we know what the answer is. So that's a really brilliant thing. Greenberger, Horn, Zeilinger.
So, when attempting to unify Einstein's geometric understanding of gravity and space and time with a discrete quantum understanding of reality, I know string theory is the most popular, or the most popular in pop culture, I would say. Could you describe how that, what is string theory and how does that reconcile the two? I know this is a very complicated, very technical question, so...
Right.
In a simple way.
It's hard to make a connection between the objectives of string theory and what and how it resolves this question, because it really hasn't resolved this question.
Okay. That's fair.
Okay, so string theory is an attempt to whitewash the difference between all the fundamental constituents of nature. It's getting rid of the distinction between, what you mean by this kind of particle or that kind. All they are different vibrations of a string.
Okay.
And by looking at the problem in that way, you've unified the whole description.
How is gravity described? The geometry of space and time, how is that described
in string theory?
Yeah.
Well, that's sort of the problem.
Yeah, they haven't really... there may not even be an answer to this question, but how are they attempting to describe it?
Let me just answer let's just go with the first one first. So
Yeah.
If you think as modes of a string, there are certain equations that you can write down which represent the tension of the string, the energy modes of the string. But there is no real way of putting that together with gravity. In other words, what is the real theory of quantum mechanics and gravity? We know that general relativity at the smallest length scales doesn't include, well, it can't, it's just a classical theory. But the simplest way to think of that is just consider 2 electrons impinging on a black hole. Once you get below the event horizon, they collapse at the center of the black hole. If the electrons are in the same spin state, We know that quantum mechanics tells us they can't go into they can't occupy the same space. But there's nothing in general relativity that's preventing that. So we know that at some length scale, something has to prevent this. And that is where quantum gravity comes in. So we know there has to be a failure of of general relativity at the smallest length scales that permits things like the Pauli exclusion.
Yeah.
That's why we know there has to be a theory such as quantum gravity. The most successful attempt so far, at least our best understanding of quantum gravity so far, is this thing called the ADS-CFT conjecture, which is an attempt to understand quantum field theory as a boundary effect of gravity. So you hear a lot about this. Are we getting close to the? Oh boy, over.
Okay.
Yeah.
Okay. I have two more important questions.
Okay. So let me just say, as a boundary effect, and so this is all based on the fact that so a boundary effect. Let me say exactly what this is. That if you consider a space-time, and you ask the question, what's the boundary of it? The rules for interpreting what's going on in the boundary all obey quantum mechanics. And so this is the holographic principle that
I was going to
so the holographic principle is our best understanding. And what it does is it maps a theory of gravity in a certain number of dimensions, and the boundary of that, so the thing in the lower dimension is is the quantum field theory.
Yeah.
So it unifies to some extent quantum field theory and gravity, and it's saying that the strongly interacting degrees of freedom live at the boundary, but you don't have to worry about those. All you need to do is just go and solve this bulk gravity problem, and that's the reason. So if you look at quantum mechanics in one lower dimension, quantum mechanics lives in one lower dimension, and that's the reason why it's difficult. If you were to solve that problem in a higher dimension, it would become a non-interacting problem of gravity.
Okay.
So,
well, I know you have to go, so I have one more. I want to end on a quote that I thought was relevant to what we're talking about. This is from Heisenberg, and he says, "We have to remember that what we observe is not nature herself, but nature exposed to our method of questioning."
Yes, that is correct.
Are we asking the right questions?
Well, you see, that's what I said. Because
is that science?
Yeah. Philosophy helps you. I think philosophy helps you ask the right questions.
Yeah.
And that's why I have found that my background in philosophy has definitely helped me. I don't think I would be going into ADS-CFT if it weren't for. I mean, I try to ask questions about unification and ways to combine two disparate things. And always going for the deeper thing. And Heisenberg had a very open mind. I mean, that uncertainty principle, that was fundamental.
Yeah.
And facing up to it is really telling you about the limitations of nature itself. I see why he said it. Because he was saying that nature can only place limitations on your ability to know.
To understand.
Yes. That's why he said it. And that might be that limitation is a fundamental principle of nature. The uncertainty principle.
That'll keep you up at night thinking about that. Why does that exist?
That's a good place to stop.
Okay.